Today we're going to talk about this idea of linearization, and let's come back to our old friend x squared. And don't we know by now how to find the tangent line to this function? If I wanted to consider the point 1, 1, couldn't I find the equation of the tangent line pretty quickly on this simple little function? Right? I would find the derivative f prime of x equals 2x, right? And then I would need to find the slope f prime of 1, which is 2 times 1, which is 2. That's my slope of the tangent line at the point 1. And then what would I do? Wouldn't I need to use this, our old friend, the point slope equation? And I would do I'm not going to go through all of that because you know what to do. I would plug in the point 1, 1, plug this in for x, this in for y, and so on. But what you get is y equals 2x minus 1. Okay? Now, let's go to the graphing calculator for a second. And let's graph x squared. And then let's graph the 2x minus 1. And in y2, we're going to put 2x minus 1. Now, let's just kind of close the window down a little bit. Let's maybe make it negative 2 to maybe 5. And I don't need all these negatives down here. Negative 2 to maybe 8 or something. So there's my original function. And there's my tangent line. So that worked out pretty good, right? Looks like a good tangent line. Now, let's do something else. Let's come back to my main page. Now, I want us to graph. Let's now graph into y3. Let's graph x squared minus 2x minus 1 in parentheses. Now, what am I doing there? Aren't I subtracting the tangent line function from the original? All right. So let's go back to my graphing calculator. Go to y equals. And let's graph what I said there, x squared minus, in parentheses, 2x minus 1. And let's graph it. Now, it's a parabola, but here's the question. Weren't we working with the point, the x-coordinate of 1? What is the value of this function when x is 1? This one I just plugged in. What's the value of it? It's 0, isn't it? Get it in here where I can draw on it. Okay, if I look at this new function that I just plugged in, when I get close to 1 here, its value is 0. Why is that? This thing, couldn't we say the limit of this thing as x approaches 0 is equal to 0? Right? Why did that happen? It happened because as we get close to 0, don't these two functions, both x squared and 2x minus 1, don't they approach the same value? Right? Don't they approach the same value? It's a tangent line. Remember what this is. This is a tangent line. So when I get close to 1, right here I'm looking at the tangent line. When I get close to 1, they approach the same value. That's why when I just subtracted one from the other, when I get close to 1, this thing approaches 0. Because in other words, as I get close to 1, they're kind of becoming the same thing. Watch for a second. Let's go back to the graphing calculator. Let's go back to my y equals screen and take out that y3. We don't need it in there anymore. And let's go to my window. And let's close down the window to 0.5. Oops. 0.5 to 1.5. And let's make my y minimum like 0 to 4. We'll just go to 3. That should be enough. Watch what happens. There's the x squared function, and there's the tangent line. When I zoom in like that, don't they start looking like the same line? And that, my friends, is the concept of linearization. Is the idea that, get back to where I can write on something here. It's the idea that when we get really close to a specific x value, okay, both functions start looking like the tangent line. That is the idea of linearization. If I look at that graph that I just pasted in there, this top one is x squared. The bottom one is my tangent line, 2x minus 1. But look right here at that section. Don't they look the same? Okay? So it's the idea that as we get close to the tangent line, both the original function and the tangent line kind of start looking the same. They start looking like the tangent line. All right? So let's kind of derive, we need to derive an equation here. Okay? Definition of linearization. Let's start with my old friend, the point-slope equation. Okay, and let's let x1 be equal to a. So if x1 is equal to a, then wouldn't y1 be equal to f of a? Doesn't that make sense? Right? So let's plug those in now. We're going to plug this in here, and I'm going to plug this in there. Now I have y minus f of a equals m times x minus a. And let's solve this thing for a. Okay. If I solve this thing for a, I would add f of a to both sides. So I have that y equals f of a plus m times x minus a. We're just about done. We need to make one more substitution. when I find this slope of a tangent line right here, what have we learned in calculus? How can I find the slope of the tangent line? Find the derivative and then plug in the value, right? So this thing right here, m is equal to f prime of a. That's something we know to be true. So guess what we've got now? Y equals f of a plus f prime of a times x minus a. And that, everybody, is what we call the linearization of a function. Okay? This is the linearization. Let's write it, we can go ahead and label it. This is the linearization. And let's make kind of a summary statement. We'll say definition. If the function is differentiable at x equals a, then the approximating function and the approximating function is the one we just derived. The approximating function L of x, I'm using L for linearization, equal to f of a plus f prime of a times x minus a is the linearization of f at a. And I'll pause the video and give you a second to write that down. Okay, and by the way, this is a quote mark here. We're not talking about f double prime. Let's go back to my original problem to just kind of see how this thing would work out. My original function was x squared. What was my a? Wasn't it 1? Right? On my original problem that we started the day with. So if I wanted to find the linearization of x squared at 1, I would use L of x equals f of 1 plus f prime of 1 times x minus 1. Now, what would f prime of 1 be? Well, f of x is 2x, so f prime of x is 2x. F prime of 1 would be 2. So now I would have a 2 here, an x minus 1 there. What's f of 1 back in the original function? 1. And so there's my linearization, and I could clean that up. This is 2x minus 2. So it's going to be, isn't it going to be 2x minus 1? Which turned out to be our tangent line. It's actually, in a way, a shortcut to the tangent line. Okay? So there is my linearization. Okay? So let's look at an example here. Find the linearization. Yes, it is. It's kind of a shortcut to the tangent line. And check graphically. Let's use cosine of x. And we're going to do this at x equals pi halves. So we're looking for the linearization of the cosine of x at pi halves. So we're going to start with my linearization formula. L of x equals f of a plus f prime of a times x minus a. It's a good formula to learn. Comes in handy a lot of times, and it does show up on the exam. So what is my a? Isn't it pi halves? So this is going to be the cosine of pi halves here. And what is the cosine of pi halves? 0. All right, so this is going to be 0 here at the beginning. What is my derivative of this function? The negative sine of x. So now I'm going to add the negative sine of pi halves, and that's going to be times x minus pi halves. The sine of pi halves is 1. If it's negative, it's going to be negative 1. So this is going to be negative 1 times x minus pi halves. Or I could say that my linearization is negative x plus pi halves. Now we're told to check this graphically. So let's go to the graphing calculator and see if this is a good linearization. First, make sure you're in radian mode. And I am, because we're graphing a trig function. Clear out our other things here. We were working with the cosine of x, so I will first graph the cosine of x. And then my linearization, which was negative x plus pi halves, negative x plus pi divided by 2. Now, which point, we were looking for the linearization at pi halves, weren't we? So when you do your window, all right, I think probably 0.5 is okay. Isn't pi halves 1.57? So maybe, why don't we just go to pi? 3.14. And maybe we'll make my scale the pi halves, 1.57. And if I remember some things about the trig functions, they don't go above 1. So maybe we'll just go like negative 0.5 and go up to like 1.3 or something, just enough to see it. And let's see if I'm going to get a good linearization. There's the cosine function, and there's my linearization laying right on top of it. So everything checks out, and that problem is done. Now, let me give you one more thing before we quit today. And it is what I would call an important linear approximation. It's nothing more than just kind of a shortcut, I guess you could say. If I have 1 plus x to the k power, a linear approximation, a good linear approximation of that is 1 plus kx. What do I mean? Let's do an example. Let's say that I had the square root of 1 plus x. Well, isn't that the same thing as 1 plus x to the 1/2? So I could say that a good linear approximation of this function is 1 plus 1/2 x. Okay, on this little linear approximation, there's one little important note that we need to make. This is for values of x close to 0. In other words, these two resemble each other when we get close to 0, when we get really small numbers. Why don't we try to, how about 0.1? Okay, let's just kind of verify this. 1 plus 0.1 to the 1/2 power. And let's compare that to 1 plus 1/2 times 0.1. Let's see what we get using the calculator on both of those. This is going to be the square root of 1.1, right? And so let's see what that decimal approximation is. Square root of 1.1 is 1.0488. So this is 1.0488. Now let's go over to my other one and find half of 0.1 and add 1 to it. Okay, so 0.1 divided by 2 is that, and add 1 to it.
What?
And aren't they very, very close to one another? 1.05. Nice little example of how those two, as we get x values close to 0, approach the same thing. And we're going to stop there for today.